Hi guys, welcome to Maths Heroes. So today I'm going to be taking you guys through NCEA Level 2 2024 tricky problem that top students failed. I'm going to solve and explain it. It's question 1d, the one for the cylindrical cup, and I am Rue the tutor. Okay, without any further ado, let's get into it. Okay, I got my pointer here. So as you can see, I'm just going to read through the question and please follow with me. So a drink manufacturer would like to start a new line of cylindrical cups that are designed to keep hot liquids warm for as long as possible. To do this, they wish to minimize the surface area of the new cup, which includes a lid. They would like the cup to hold a volume of 500 milliliters and be cylindrical in shape. Calculate the dimensions of the cylinder that would satisfy the above conditions. The volume of the cylinder V is equals to pi r squared h, and surface area of the cylinder SA is equals to 2 pi r squared plus 2 pi r h. Okay, so we know where we get these formula from. This is the basic or the simple volume for a cylinder. We simply say the area of the face multiplied by the height. That's how we get this. And then for the surface area, you want to find out what the surface area is of the shape itself. In this case, we've been told that it's closed at the top, but if it was just a normal cup, it would be open at the top. So we wouldn't have this, but since it's closed at the top, it's going to be this area, right, which is pi r squared multiplied by 2 for the area of the bottom. And then for the area, the outside area, right, what we're going to have is the area of the circumference, right, of the circle at the top multiplied by the height, because if you open it out, it looks like a square. So it's like multiplying the length times the width. But in this case, the square is folded into a circle, or if you take a piece of paper and you round it into it, becomes a cylinder. So in a sense, it's just multiplying the area of your circumference. Okay, no, the distance, not the area, the distance of your circumference by your height, so that you can get the surface area of the outside of the cylinder. Excuse me for that. Okay, so let's move on. Okay, so we're going to move into our solution. So first, what do we know? We know that our volume is 500, so we equate that to the equation for the volume of the cylinder. So we know that V is equals to 500, therefore 500 is equals to pi r squared h. Then our second equation, which we were given, luckily, it's going to be surface area is equals to 2 pi r squared plus 2 pi r h. Okay, excuse me. Okay, so moving on, right? We make h the subject of the formula for equation 1 by dividing both sides by pi r squared, and this then gives us h is equals to 500 over pi r squared. Then we substitute that into expression, and we substitute our expression into equation 2. So the reason why we're doing this is because we are trying to get one equation in terms of r. So we want to eliminate h, right? So how do we eliminate h? We make h the subject of the formula for this equation. Subject of the formula should be something you learned back in level 1, okay? So we make h the subject of the formula here, and then we then substitute h into equation 2, okay? Then what happens when we do that? If we were to substitute h, right, into this equation here, what we then get is the surface area is equals to 2 pi r squared plus 2 pi r multiplied by 500 over pi r squared, right? So what do we then do at this stage? Okay, what we then do at this stage, right? What do we do at this stage? Let me just quickly grab a marker. So what we do at this stage is we cancel out the r, right? And then just remove this power. Then we cancel out our pi, right? And then 2 multiplies the 500, agreed? 2 multiplies the 500. So what we then get after carrying out these operations is, obviously, like I just said, r and pi at the top cancel out, and then we multiply the 2 by the 500 to give us surface area is now equal to 2 pi r multiplied by 1000 over r. Okay, very, very, very simple, not even complicated at all. So that is what we do, right? And then now that we have this expression, then we actually get into the mathematical problem, or what we're trying to achieve mathematically. Okay, so this is where the math trick comes in to play. So let's go back to our principles of differentiation. Okay, so this then becomes a differentiation problem. It becomes a differentiation problem because we are trying to optimize. So there's a topic in differentiation called optimization, where you look for maximum and minimum. So that's the concept you now apply at this stage going forward. And for me, this was the most tricky part of the question, because I don't know if optimization is taught at level 2, but I know for A level you do learn optimization as part of calculus for your calculus and stats paper. Okay, so moving on. Okay, so optimization, right? For example, the graph of a function y, f of x, has a local maximum at the point where the graph changes or increases and decreases. I'm going to show this graphically. At this point, the tangent has zero slope, and the graph has a local minimum at the point where the graph changes from decreasing to increasing again. At this point, the tangent has a slope of 0. Okay, let me show you what I mean. Right? So what I'm saying is we have a graph, right? So this is if we are looking for the maximum, it's here. So the graph has a maximum when so here it's what? It's turning from increasing, it's starting to decrease, and it has a minimum here where it is going from decreasing to increasing. So this is what I was trying to explain in the previous paragraph, okay? Just to go further into that, we can see our behavior. So the question is, how do we find these minimum and maximum? That is where it comes in, right? So how we find a local maximum, right? The slope, the derivative, which is obviously what? The slope of the tangent, right? At a point, right, slightly to the left of the maximum is a point xo. And how do we find this point? It is simply the derivative of the function, right? So this is for your maximum. And then for your minimum, like the local minimum, it's a negative decrease. It is also simply just you derive, but typically it's going to be less than 0, it's going to be greater than 0. So for a derivative, right, the slope of a point at a maximum point xo, if you still divide and you equate it to 0, whatever the f of x, the function f of x, right, you obviously you differentiate it, right, and that derivative, right, you equate it to 0. If you equate it to 0, whatever you find the value of x to be, that is the value at this point. That is the value at this point, what you find x to be. So in this case, we're going to be applying this. This is the principle we're going to be using. This one. We're not going to be using this one, and we're not going to be using this one. We're not going to be doing the derivative of slope tangent at a point slightly to the right of the maximum, because you have points here and you have points here. It's entirely up to you. But we are going to be using this point for the maximum and minimum, okay? And so this is the concept, right? So this is where this comes from. This is where optimization comes from. So now let me touch on optimization. Okay, so optimization in theory and applications, we often want to maximize or minimize some quantity, right? I'm an engineer, so obviously an engineer may want to maximize the speed of a new computer or minimize the heat produced by an application. A manufacturer may want to maximize profits and market share or minimize waste. In this case, it's the manufacturer trying to minimize waste. They want to know what would be the most efficient dimensions for us to get a 500 ml cup and limit surface area so that the cup does not lose heat to a large surface area. That's actually the reason why they would be doing that, because if your surface area is large, obviously by laws of thermodynamics, you're going to lose more heat to entropy, right? I'm sure the physics guys know what I'm talking about. So that is the basis of it. So they want us very minimize surface area so that they don't lose too much heat, and the cup is more efficient because one, it's able to retain as much heat so that your cup remains warm as possible. Think of it like those that's called Stanley cups that I think had a craze. So you think, or imagine this is a manufacturer, those Stanley guys, and they're trying to create a Stanley cup that is able to maximize heat at a certain volume, or to maximize heat retention at a certain volume, or to reduce heat loss, because actually you actually can't keep heat, so you'll always be losing heat to entropy through the universe. But no, let's not get into that, since I think it's above your level. But that's the concept of it. Okay, so moving on, that is the basis. So we're simply trying to optimize. And how do we optimize? We optimize through using a differentiation to find the maximum minimum. That's how you optimize. So in a nutshell, we are simply trying to use optimization to find out what dimensions would be best for our cup. Okay. Okay, coming back to our solution. So moving on. So what we then do now is we have our function, our surface area 2 pi r squared plus 100 over r. I think I've showed you guys how we get to this, right? So this is the function is in terms of r, right? So what we do then now is we find the optimum minimum for r, which gives us our required volume and surface area, right? So f of r is 2 pi r squared plus 100 over r. It's the same. It's the same as saying SA is equal to 2 pi r squared plus 100 over r, because this is just a function. It's just an f of r. It's just a function, right? So what we then do is if we differentiate this function and equate it to 0, we will either find the minimum or maximum of that expression, right? And given that this is an r, this is an r squared, what does an r squared graph look like? An r squared graph is concave. Let me just try and quickly draw that. What does an r squared value look like, right? Or an r squared graph looks, I don't know why that's not working. Let me try that again. Maybe I'm just having one of those days. Okay. So what does an r squared graph look like? We already know an r squared graph looks like this, right? This is what it's concave, right? This being your x, and this being your y, right? Because it's r squared. So we know it's going to be some minimum. Might not necessarily be on this point. It will most probably look more like this. Let's say, right? And the sum point here will be the value you want. Not exactly. Some point here will be the value you want. Or some point here, because it's going to be in the terms of x. But this is actually going to be r, right? But, makes no difference. But we'll, our x is r in this case, interchangeably. But this is what we're trying to do. From the r squared, we know we're going to be finding a minimum, because we know that if it's r squared, or for example, if it's x squared, it's just like the x squared graph, you know that it's going to be a u like this, right? It's going to be concave, okay? So moving on from that, that is how we know for sure that we're going to be finding a minimum value, because we're looking at the expression. So obviously you need to understand what's going on. That's why I'm taking my time trying to explain. Okay, so moving on. Okay, let me rub all of that out so that I don't confuse you guys. So yes, we obviously then differentiate the expression. And then if we differentiate our expression, so we're gonna say d of SA in terms of dr, right? We want to differentiate. So for our differentiation, we know what happens, right? For our differentiation, it's very obvious what happens. Okay, for our differentiation, we know exactly what happens. What happens for our differentiation is we have our r here, right? So this 2 comes and multiplies the 2 here, right? And obviously this exponent is just subtracted by 1, right? So what that gives us, it's going to give us a 2, right? Multiplied by 2. This is a multiplication, so not an x, excuse me. By pi r, because we've removed the exponent, and this is just like r to the power 1, and we don't need to write the power. And then what happens with our 1000, right? This is the same as saying 1000 to the power r minus 1. So the minus multiplies the minus 1, right? Multiplies our 1000, right? And then by the r, it's going to be minus 1 plus another minus 1, which will give us minus 2, right? So it comes to this, right? That being said, r to the power minus 2 is just the same as saying r to the power minus 2 is the same as saying, obviously, it's the same as saying 1000, right? Over r squared. It's the same thing, right? So that's how we carry that out or that's how we simplify that. So let's move on. Continuing our solution, right? We equate our ds dr to 0, then solve for r to get the minimum value. So simplifying, multiplying the 2 by the 4, we get 4 pi r squared minus 100 over r squared, right? And we equate that to 0 because sa over dr, right? we equate that to 0, and then we get that, right? Then the last piece is simply simplifying this expression to get r, okay? So what we then do is we move r here to the other side. If we move r to the other side, this becomes minus 4 pi r. If we multiply everything by the negative sign, we get 4 pi r is equals to 100 over r squared, right? And then what do we do here? Now, what we want to do is we multiply both sides by r squared. So if we multiply both sides by r squared, okay, let me just write it as we go so that you guys don't get confused. Okay, so what happens here is, okay, this goes to the other side, right? And then we end up here, then we multiply both sides by what? By r squared. So we cancel this out, and then so what we end up being left with, multiply both sides, what we end up being left with is this, right? And then we simply divide both sides, right, by 4 pi by 4 pi, right? We divide both sides by 4 pi, and then we cube because we're left with r cubed. And then what do we get for r? We get 4.3, right? And then we can substitute r into h, into the expression we had for h, to get 8.6 centimeters, right? Mind you, we can also do this process, everything we did, we can do it for h and go the other way around. And we will still be able to find what h is, 8.6, and then we can come back and substitute to find out what r is. But from the look of the equation, substituting for h would be a bit more difficult, create very difficult equations to solve. So most probably, if you would attempted that in the exam, you would find out very quickly that you've gone down a very dark path, and you'd most probably want to come back to using r. That's how I see it, and that's how I'm looking at it. Okay. So for me, this question was very difficult. It can easily be a first year, a university calculus question. But I believe A-level students would be fine because, optimization is covered as a topic. Dr. Chris Knox, who I believe is a professor, also has a video of this solution. Check it out. I think it's on the New Zealand Herald. One of my students sent me this question. I was helping them prepare. If you guys have any more questions, difficult questions, please send them to my email, as you can see there. I'm always happy to help. I'm also available on SuperProf for private and group tutoring. The link is in the description. So that's all. Thank you guys for listening. I hope I helped. I hope I assisted. Thank you so much. Until next time, cheers.